Hello, everyone. My name is Cheng Jun. I'm from Zhejiang University, Ningbo Institute of Technology. Currently, I'm visiting JAEA. So, first of all, I want to thank the organizers for providing this opportunity to give a talk and to present our recent study. So today I want to talk about the supercritically charged objects and the electron positron pair creation. Uh, these are my collaborators. You may find some of them in this conference. So over the decades, people have been curious about the possible existence of objects heavier than the currently known nuclear, and there exist various possibilities. Uh, for example, since the 1960s, nuclear physics suggested that there may exist unusually stable or long-lived superheavy nuclei due to quantum shell effect, namely this island of stability. Through tremendous efforts, people have synthesized superheavy elements with proton number less than 118, and by fusing two nuclei into one. Meanwhile, there exist other possibilities. It was argued that strange quark matter comprised of deconfined U, D, S quarks may be more stable than nuclear matter. Then there could exist small objects made from strange quark matter, which is often referred to as strangelets. Nevertheless, the mass of strange quarks may be too strong to exist in strangelets, which leads to the possible existence of UD quark matter nuggets that does not contain any strange quarks. And alternatively, instead of deconfined quark matter, quarks can be confined within clusters, namely strangens. Due to the attractive interaction among strangens, there could exist stable stranger matter and stranger nuggets. So for more details, please refer to Professor Xu's talk. And despite the great success in producing superheavy elements with heavy ion collisions, synthesizing heavier ones is extremely difficult, which is already approaching the limit of our experimental capabilities. Similar situation may be expected for more exotic objects such as stringlets, 3D quark nuggets, and stringent nuggets, since they have never been observed experimentally. The situation may be very different in astrophysical environment. For example, in the crust region of neutron stars, there already exist large nuclei with proton number already reaching 1000. Such a large nucleus can be released in violent astrophysical instance. For example, the binary neutron star merger event, which will eject a large amount of those objects through tidal disruption and squeezing. Similar situations are expected for strangelets, UD quark matter nuggets, stranger nuggets, if the merging compact stars are actually stranger stars, non-stranger quark stars, or stranger stars. Once those objects are created, it is likely that their electrons will be stripped away through various ionization mechanisms. Then those objects become supercritically charged, which will emit positrons by Swinger mechanism. In such cases, it is possible to identify those objects by searching for photons that created by positron annihilation, which are typically 511 keV gamma rays. In fact, we have already observed such photons in the center region of our galaxy. Uh, where this 511 keV was observed. And this actually was recently used as a tracer for binary neutron star merger events. And meanwhile, in various galaxy and galaxy clusters, people have found faint emission line and absorption line in X-ray spectrum, which was considered as a decay of dark matter particles in various publications. However, according to Professor Han, Professor Ruffini, and Professor Xia's work, those emission lines could actually, due to the back reaction of electron-positron pairs, which emits electromagnetic radiation, peaked around 4 keV. And in such cases, to investigate those objects, we expand the energy per baryon of nuclear matter, strange quark matter, UD quark matter, and strange matter to the second order. So when the baryon number equals to N0 and the charge fraction equals to Fz0, then the energy per baryon is at its minimum, which is E0. And those parameters are fixed according to previous investigations, where we have taken their typical values. Then the baryon number, the net charge number, the total charge number with electrons, and the electron number, as well as their mass, can be obtained based on this Thomas Fermi approximation, where they all have this local density distributions. And at a given total baryon number and the charge numbers, the structure of those objects can be obtained by minimizing the mass. Then basically we find that this kind of distribution, the most stable density distribution, follows the constancy of the chemical potential of baryons and electrons. And meanwhile, the stability of the core surface is required by this formula, where this R is the core radius and sigma is the surface tension of the object. And the Coulomb potential is obtained by solving the quotient equation. So by solving all these equations, minimizing the mass altogether, then we can obtain the properties of those heavy objects. Here, I present you the energy per baryon of super heavy elements, strangelets, UD quark matter nuggets, stranger nuggets. And the solid, this solid square corresponds to the experimental values of beta stable nuclei, where here is iron 56, which is the most stable nucleus. And as you might have noticed, our calculation will reproduce the experimental data. And for other exotic objects, they may become absolutely stable once their energy per baryon became smaller than 930 MeV, which is energy per baryon of iron 56. The corresponding minimum baryon number for UD quark matter nuggets, strangelets, and stranger nuggets are given here, which is respectively those values. And of course, I should mention that those values are not final because none of those objects have ever been observed. Next, let's talk about the charge properties of those objects. Basically, for each object, it is surrounded by an electron cloud, which is crucial to determine its charge property. At a given Coulomb field, electrons feel in the Fermi sea with the boundary of electrons at Re. And the top of the Fermi sea corresponds to the electron chemical potential, this mu E bar. Because there's no electrons here, then the Coulomb field at this electron vacuum boundary is simply Q over Re, where this Q is the charge number. Then a simple relation between this Q, Re, and the mu E can be obtained. So this is a universal relation. And if the chemical potential is below the Dirac sea, namely minus Me minus electron mass, then electrons will penetrate the barrier and occupying the empty states above the Fermi sea, leaving behind a hole in the Dirac sea, corresponding to a positron. So this is basically the well-known Swinger process for electron-positron pair creation, which is otherwise impossible if the top of the Fermi sea is larger than minus Me, as demanded by the Pauli exclusion principle. The decay rate can then be estimated using this JWKB approximation, where the probability of penetrating the barrier is obtained by this formula. And here, this Fe represents the empty states in the Fermi-Dirac distribution. If we take this Me bar equals to minus Me, the maximum charge an object can carry without causing electron-positron pair creation can be estimated. So here I present to you the obtained maximum charge, and here this Z represents the net charge without electrons. So despite the large difference on the net charge of each type of objects, the obtained maximum charge is converging at large baryon numbers. And if an object carries more charge than the critical value Q, then electron-positron pair creation will start. However, in order for such process to take place, those objects need to be large enough, where here in those regions it's not possible. And the critical charge and the baryon numbers are then estimated with this formula. Here, the number 2 is adopted since the electrons are degenerate in spin. And these are the obtained decay rates of electron-positron pair creation for supercritically charged objects with a fixed net charge number. As electron-positron pairs are being created, the charge number of each object is decreasing. So basically, the positrons were emitted and the electrons were captured. According to our estimation, most positrons are emitted at less than 10 to the minus 15 seconds, basically due to this large decay rate. However, for large objects, the decay rates decrease very quickly. Then in those regions, the decay rate is very slow. So this means a very long-lasting positron-electron creation. To show this more clearly, here I present you the decay rates for supercritically charged objects with a core radius being 1000 Fermi, which becomes extremely small as charge numbers decreases. And in this region, so the electron-positron pair creation continues, but at a very slow rate. So if we assume the ejected mass during the merger of binary compact stars is 1 million solar mass for the supercritical charged objects. Then the energy released due to the electron-positron pair creation and annihilation can be estimated. And comparing with the observational isotropic energy release of GRB 1170817A, our estimation of finite nuclear and UD quark matter nuggets gives somewhat similar value, while those with strangeness give smaller energy release. Nevertheless, I should mention there may be other important energy sources, for example, thermonuclear reactions, the strong decay of those objects, and thermal radiation, etc. So here comes to the summary. Based on the Thomas Fermi approximation, we have studied the stability and electron-positron pair creation of supercritical charged objects. And we find that there exists a universal relation between the charge and the radius of electrons, as well as the chemical potential of electrons. And we find that the electron-positron pair creation rate estimated by JWKB approximation. And also, most of the electrons are emitted very quickly within 10 to the minus 15 seconds. But there also exists a long-lasting positron emission, which is very likely for very large objects. And the production of electron-positron pairs can thus be responsible for the short gamma ray burst, the 511 keV continuum emission, the narrow faint emission and absorption lines in X-ray spectra from galaxies and galaxy clusters. And finally, I present our result in a table where you may find the charge properties as well as their stability. So that's all. Thank you all for listening.